Hello everybody, it's me, Andy. This third video in the series on neurodynamics will introduce some mathematical tools that you'll see a lot in your upcoming studies. It is also the last video, which is meant to prepare you for your first lectures. Main players of this video will be the exponential function as well as differential equations. I will not focus on giving you technical details about those two mathematical tools. Rather, my primary goal will be to present you with reasons on why I think differential equations are not only concise, but also elegant and beautiful. As you may know by now, neurons behave in complicated ways. One reason for this complexity is the dependence of the neuron's current state on its previous states. Put differently, how a neuron will behave depends on how it did behave in the past. This is actually the one fact which this video will try to shine light on: the dependence of the future on the past. The future of X is given by what happened to X in the past. Let's have a look at two examples which are less complex than the behavior of a neuron. Say you want to describe the growth of a population. Could be anything: humans, rabbits, ants, doesn't matter. When you start observing the population, there are, say, 2,000 guys. And since you're an optimistic person, you neglect all possibly negative factors and only consider the birth rate, say 1% per time unit. In that scenario, this is what your population graph might look like. Okay, another example. Imagine a bucket losing water through a small hole that you drilled into its bottom. At the beginning, there's a lot of water above the hole, say 4 liters, which is pushing water out of that hole. As time goes by, there will be less water in the bucket. Less water in the bucket causes the pressure onto the water at the hole to decrease, so the bucket will lose water more and more slowly. The corresponding graph might look something like this. Okay, enough examples. What am I aiming for? No matter which of those two examples you consider, both can be modeled using the exponential function. The positive version of the exponential function is growing really fast. Likewise, the negative version is decaying like crazy. You probably already know the exponential function, or E, from high school or from other courses. So let's have a quick recap and then move on to the exciting stuff of this video: differential equations. The recap. First, make sure that you know what people are referring to when they talk about the exponential function. Rather than knowing facts about it by heart, it'd be great if you would have an intuitive understanding of this special function. Next, try to model those examples I gave you at the beginning. The actual numbers of your model don't really matter. It's the type and the look of the function which determines its shape. Alright, have a go and proceed as soon as you feel ready. Spoiler alert, if you go on now, you'll see my models of the examples. So you won't be able to do this exercise ever again. First, here are some resources if you want more information. Khan Academy has a whole playlist, including exercises, on exponential growth and decay. Maybe a good starting point. Gilbert Strang, one of my favorite online math professors, is also exploring the exponential function, but in a somewhat more rigorous way. And finally, Dr. Bartlett. Well, the video is really low quality, but he addresses a point which seems to be neglected quite often. Okay, so much for the videos. My favorite text resource for intuitively understanding math concepts is a website by Khalid Azad. He has a whole series of articles on growth, E, and logarithms. Also, his webpage is a good resource for some other concepts which you will encounter in your studies of neuronal dynamics. Complex numbers and eigenvectors are two examples. And as promised, here are my attempts to model the examples from the beginning. On the left, the model for population growth. The starting value of 2,000 individuals is multiplied by the growth factor, that is e to the power of birth rate times time. If I'm talking Arabic to you, Khalid's article on betterexplained.com might be helpful. Okay, let's move on. On the right, you'll see the model for the leaky water bucket. Essentially the same. The starting value of 4 liters is multiplied by a decaying factor, that is e to the power of some negative rate, called r, times time. Okay, now let's take the next step and consider differential equations. The exponential function satisfies the following relationship. The derivative of e to the t is identical to the value of e to the t. This might look profound, but it is what I wanted to point at right from the beginning. It is so elegant a statement, connecting past and future states of a function. Equations which relate a function to its derivatives are called differential equations. Finally, in terms of neurodynamics, we're going to use it like this, maybe, or more precisely like this, where f is some kind of function. What this equation is saying is that at each instant, the membrane potential of a neuron is changing depending on its current membrane potential. Do you see how this connects past and future states? On the left you see what is representing the future, the change that is going to happen. And on the right you see the past. Well, at least from the point of view of the differential from the left-hand side. Okay, let me try to drive this point home. I want to be more explicit about the connection between the exponential function and differential equations. It turns out you can use both to model the exact same situations. I'll prove it to you. Here's the population growth model which I previously introduced. First, try yourself. Express this model in terms of a differential equation. Well, here's how I would do it. Maybe you start seeing the connection between differential equation and exponential function. But in case not, no problem. We have a second example. What about the leaky bucket? This was my idea for a model. What do you think? How would an equivalent model using differential equations look like? Again, here's how I would restate my own model. Seeing the same idea expressed in 2 different ways hopefully revealed some kind of connection to you between the exponential function and differential equations. Alright, I don't want to go too far. Some last ideas what you could ponder about. First, mathematicians classify differential equations into many groups. They also use some special vocabulary. So, it'd be probably helpful to know what they are talking about. Some differential equations are linear, some ordinary, and others are only partial. Oh, and while you're at it, what is the solution to a differential equation? A function or a number? As soon as you feel ready, try to convince yourself that the differential equations I used to model the previous 2 examples are indeed equivalent to the exponential functions I introduced earlier. Try to solve those 2 differential equations. And since I don't want to break with our established habits, here's a resource for more information. When it comes to mathematical education, I can only say that most of my understanding comes from Salman Khan and Khan Academy. So I have to advocate their whole course on differential equations, including videos and exercises. The course also has an introductory part, if you want to take it easy. You'll definitely won't have any difficulties finding more information on differential equations than this course on Khan Academy. So let's close the video on the mathematical foundations of neurodynamics at this point. Thanks for watching, leave a comment, and I'll see you soon.